Hello everyone. My name is Lukas Sismis, and I came to talk to you a bit about my use of Regex device offload, especially in combination with acceleration of network applications. I'm from Slovakia, but I live in Czech Republic, so welcome. Okay, what was the main motivation behind this work is that I generally work and I'm part of Suricata intrusion detection open source team, and pattern matching there is really a heavy operation in these systems. So it can take even 50% of the CPU time. Generally, you have packets coming from the port directly to Suricata, and they spend the processing there. This was in our analysis, but this is also supported by a different analysis that 50% is a good estimate of time spent for pattern matching. So when I learned the DPDK offers some Regex offload device, I was very enthusiastic, and initially I honestly thought it can be like a pipeline that packets would go from port through the Regex offload and into Suricata with some extra maybe metadata. What I was also enthusiastic about is that DPDK is of course the open source and vendor independent API, so it could be ported to any NIC. What I hope to deliver with this talk is my experience basically with the Regex API, what to maybe expect, and I haven't found many information from people using it, so hopefully it may be a help for future users of the Regex API. So right now, I would like to start a brief introduction to the Regex API in DPDK, then some comparison between the software and hardware offloads, and what are our current results with integrating the solution into Suricata. Okay, so the Regex API is actually in DPDK for 6 years. It's available on 2 series of cards, and that is BlueField-2 and 3, and Marvell Octane TX2. It's a leukocyte accelerator, as I soon found out. So you cannot pipeline data from port to the Regex engine, but you need to receive them on the CPU and then send them to the Regex accelerator. What are the software alternatives to the Regex matching, and what are the commonly used libraries for pattern matching is Hyperscan from Intel. There is a branch from Hyperscan called VectorScan, which is more ported for ARM architectures, and libpcre2 is for the most generic Regex support that you can have in software. The Regex API is very similar to other APIs that you know from other DPDK sub-libraries or other modules. So you have some configuration part, Ncube part, and other parts, and test Regex is the DPDK provided example application that you can get your examples from. Generally, in the first step, in the configuration step, you configure the Regex device, and then you have some set of patterns that you will want to load into the Regex device. And then, when you are using the Regex device, you generally receive, let's say, an MBUF from a port. Then you initialize the DPDK Regex ops operation structure with the reference to the MBUF and some other configuration fields, and then you enqueue the operation to the Regex device. What I would like to maybe highlight here, and what was a bit confusing for me at the start, is when you actually let's say, transmit an MBUF to a port, or you are enqueuing object to the RTE ring, you should be like losing reference to the object. But this regex ops are just like helper objects. And in the enqueue operations, they are actually just copied to some vendor-specific object, and you are still reusing the regex ops. And then when the regex operation is received by the regex device, the device then reads the data that it needs to scan with the patterns it needs to inspect, and then it returns us the results, basically. It's a synchronous API, so you enqueue the operation and then later on you dequeue when the device returns the results. What are the target applications that regex API was developed, the intent was developed in? It was exactly the intrusion detection system, intrusion prevention system, web application firewall, so basically some data-heavy operations, or maybe even host memory analyzers, so the application might not need to be directly network related. They might be just data mining or the memory analyzing applications as well. I haven't found any basically application that would publicly admit that use the regex API. So it's still, I think, looking for its very good use. But I found some exotic features, let's say, that could be helpful. And that is external buffer support. So you don't need to create special objects. You can reference the current MBUFs. Or part of them with the external buffers, or you can change them, and the regex device will still should inspect it as usual. I tried the external buffer support, but I didn't have luck with the BlueField RXP. Okay, so previously I mentioned that there are the BlueField-3 and the Marvel NICs. BlueField-2 is quite common with BlueField-3 as well. We tried to also get the Marvel, but we couldn't get it. We either had no reply or it wasn't in stock. But from I will present some let's say performance testing that we did. And from my information, it should the same regex engine should be actually in the Marvel NIC as well. And my assumption is that as in Mellanox or NVIDIA bought the regex engine company, the Marvel lost the opportunity to have the regex engine in there. To introduce the card that we were working with mainly, it's the NVIDIA BlueField-2. It's the data processing unit, which I assume most of you know. But for us, it was really the regular expression engine in there that was of our interest. Here in this diagram, here we have, on the left, we have network port, and it generally goes to the host, let's say. And here is the regex engine. It's in the Lukas Site Hardware Accelerator box. This regex engine supports a subset of the PCRE standard, so you cannot put there any kind of regular expression there, but in general it supports, the support is pretty good. Other specifications of the BlueField-2, it's 100G NIC. It has ARM cores, so you can use those as well. It's the A72 cores and 8 gigabytes of RAM. When we were kind of evaluating how to use the regex engine, we were looking for the RXP benchmarks. So the RXP is the regex engine in the BlueField-2. And we found many works that evaluated the BlueField card itself, but not the Regex engine. We found, let's say, these four main works, but all of them had very different results. So let's say the DPU bench had only 12 gigabytes of throughput, which seemed very low. Then some other works improved the throughput to 30 to 40 gigabits. And then NVIDIA provided benchmark, reported 51 gigabits. So we wanted to kind of test it ourselves. With this slide, I would like to highlight the NVIDIA's RXP bench tool for the benchmark purposes. Me personally, I spotted it a bit too late into the evaluation process, but it offers basically the connection to the RXP accelerator, to the evaluation with Hyperscan, with the software variant. It's within the Docker packages. And some tips on how to navigate within the NVIDIA docs is make sure you have the very latest version of the docs. It's not always when you click from the Google. And then suddenly, when I was on the right version of the docs, I could see that NVIDIA also published some benchmark results. And you can get the extended benchmark of the Regex engine from NVIDIA, but you need to ask and sign NDA, which we didn't want to because we wanted to also publish the results later on. So also NVIDIA, they basically had 3 data sets. It was the, let's say, Shakespeare, some port 80 and MEC CDC PCAP, and some the rows represent the rule or pattern sets that they were scanning the data sets with. And they also reported very varying throughput from only from 4 gigabits to 51 gigabits. So it depends. So we also wanted to try to test it. And in our work, we provided the open source Regex test application, which uses the DPDK Regex API and also uses the Hyperscan just so we can compare what are the results of individual pattern matching engines. And honestly, we're overloaded with the complexity. Regex engine is not easy task to benchmark. So in the end, we just went with the fairly simple benchmark of having packet gen as the packet generator, which was just generating same size packets. And as an input to the Regex engine, we were providing patterns and regexes from the intrusion detection system from Suricata. And one of the results was this throughput heat map. The X and Y axis are 2 different parameters which we were changing with packetgen, basically, and also the input rule set. So the x-axis is how many rules were loaded into the Regex engine, and y-axis is how long the inspected packet buffers or the input packets were long. And from here we can see that if you have long enough packets and not too overloaded Regex engine, then you can really achieve the 51 gigabits of throughput. But if you go lower with the packet length, or if you go higher with the rule count, then the throughput is kind of going downhill pretty fast. In here, we also compare the Regex engine versus the Hyperscan, the software alternative on two platforms. On the left, we have the ARM cores that are directly on the BlueField itself, and x86 cores on the host machine. The y-axis here is the maximum throughput, and x-axis is basically how we scale the Regex test application. The lines on the plots are the maximum throughput that the Regex engine achieved. Here it kind of copies the information, especially with the high number of patterns. If you overload the engine, then it's kind of stuck at the maximum throughput, let's say 5 to 10 gigabits. So it's definitely not recommended to use too much or too many patterns. Here I have some notes just to make sure I don't forget anything. What was very positive to see was that the Hyperscan is very well scaling with the number of cores. Let's say in x86 we can see the linear scaling with the number of cores. This scaling on the ARM and the Regex engine itself, it's not the scaling that the Regex engine would use more CPUs, but rather it's the low forwarding capacity of the ARM cores that they were just not keeping up with forwarding data to the Regex engine, and that's why the performance improves on the ARM and not on the x86. What we can see here basically, that if we compare the light orange line on x86 and light blue, that's the Hyperscan, we can see that with one core on x86 we can match the performance of around 8 x86 CPU cores. So you need 8 CPU cores for Hyperscan to match the same performance of the Regex engine, which can be pretty positive. But what is even more positive is when you look at the ARM and when you look at the light blue on ARM, it's rising pretty slowly, so you would need much more ARM cores to match the same performance as you have with the Regex engine. What is also interesting here is that Hyperscan, the latency, basically the time that you send just one operation to the Hyperscan and it returns back the result, was in this case around 3 microseconds, whereas with the Regex engine it was we had to wait for like 5 microseconds, but that is for a single synchronous operation. Where RXP can gain is because it supports the asynchronous operation. So you just tell the RXP to do its job, and then in the meantime you can do anything else. With Hyperscan you are busy doing the pattern matching, so that's why you can gain some performance with the RXP. Since you are loading the rules only in the beginning, you still want to have the rules in some smaller groups, because usually you don't want to inspect every buffer with the whole rule set. And we were wondering if we have many like little groups, the subsets, in our overall rule set, will it somehow affect the performance? And as we can see, with one group which contained all the patterns, it was 28,000 patterns, the throughput was degraded. But as soon as we divided into smaller subsets, the performance improved to the expected results around 50 gigabits per second. And even if we had 1,000 subsets, it's fine. And yeah, we don't need to worry. Now, how we implemented the regex into Suricata. So first, what is Suricata? Suricata is the open source threat detection engine. It's generally known as the intrusion detection system, so something that you mirror your traffic to. It's loaded with some security rules, inspects it, and has some outputs. Sometimes it can be in the intrusion prevention system, so lying directly in the data path or network path, but it can be also used as a library in your custom applications. Generally, people are interested in the signature alerts, so some outputs from the security rules, but it outputs other information as well. That is very useful when doing the cybersecurity operations. This is how, let's say, the rule looks like that's loaded to Suricata. It has some conditions that are logically connected with the end operation. And here we have, let's say, HTTP method get. Get is the string that you are looking for in the packet, or the rule is the string that you are looking for. What's the typical IDS processing pipeline? You receive a packet, HTTP packet. It's captured by DPDK, it's decoded, and then you have the first optimization that's usually in intrusion detection systems, that's dividing the overall security rules into smaller subsets of rules. So yeah, you don't want to inspect the UDP rules. You focus on the TCP and to server direction only rules. You can do some other kind of pre-filtering, but what we are mainly looking at is the pattern matching here in this talk. So in this orange box, the multi-pattern match is a way how you filter down only you will only inspect the rules that from which at least one pattern matched. Let's say you have multiple rules. One of the rules have the search as a pattern to find, and if you find it in the packet, as let's say here, it's good, and you can proceed with the overall evaluation. So the multi-pattern matching is the main CPU-intensive operation of the intrusion detection system, and that's what we were mainly looking at. It operates in multiple contexts. So the multi-pattern matching generally tries to be as specific as possible. So if the rule is concerned about HTTP, only is applied to HTTP packets. But packet payload is the most generic. Like when it cannot match on anything else, it fallbacks on the packet payload, and it inspects just the packet itself. And that's what actually takes the most time. When we did some performance analysis of the IDS pipeline, we have some boxes on the left, which is the I/O operation, decoding, stream reassembly. But what is the most important here is the payload multi-pattern matching pre-filters and some other pre-filters here. And this red thing is what really interests us. But why? I will just explain it in a second. So when we wanted to offload the pattern matching operation, we had some constraints to consider. I didn't mention this, but for RXP, you need to have the inspected buffers in the huge page memory. Generally, Suricata uses the regular malloc free operation. It dynamically allocates the memory during runtime. when I just converted it naively to RTE malloc, I found out that RTE malloc isn't very good at dynamic allocations that you do at the runtime. So that failed. You can also copy the desired memory to be inspected just before you send it to the RXP, to the huge page memory, but basically this copy operation was too heavy. That's why we focused mainly on the packet payloads only, because packets are residing in the huge page memory because we use DPDK. And we can send these, the packet payloads directly to the RXP engine. Then the other constraint that we had to consider was the latency of the RXP engine, and we couldn't really wait for the RXP because it's longer. It has longer latency than the Hyperscan. So that's why we opted for asynchronous offload, meaning we process packets, other packets. Meanwhile, we wait for the pattern matching results from the Regex engine. Then we also had to consider the rule set size. The rule sets in Suricata can have 50 to 100,000 rules. Those are pretty normal numbers, but those don't go directly, those are not directly searched. They are split into subgroups. And when we found out that pretty well-known detection rule set from emerging threats have around 2.4 thousand patterns, we knew we are in the safe numbers, because from the heat map we could see that we can go up to 8,000 patterns. And the packet size, we tried multiple variants, but at this time we have kind of like dynamic thresholding implemented. So if the RXP engine is not super busy, we send any packet to it, and if it's becoming more and more occupied with packets, we only send the more prospective packets, the larger packets, to the RXP. So PAMO is the let's say the proposed design, software design for Suricata. I think I basically explained this slide with the previous one. Yeah. So this is how we basically changed the operation in Suricata. In Suricata, the usual operation is run to completion. So one worker receives the packet and completely processes the packet from the start to the finish. In PAMO, as we were introducing the asynchronous operation, we pre-filter the packet, and if we see that, okay, we need to send it to the RXP engine, then we create the asynchronous job and send it to the RXP. If, let's say, the packet is only in a TCP acknowledgement, then we just finish the processing of the packet. Later on in the main processing loop, we are not only polling for packets from the port, but also from the Regex engine. And that's when we convert the results back, like we try to reinsert the packet into the usual processing pipeline, and we finish the processing. Okay, so here are some final results. The blue dots are the proposed system. The orange, what is it? Let's say rectangles are the baseline Suricata. We tried it with the emerging threats open rule set again, and some academic trace that we captured and replayed on the system. And we can see that, let's say, if we look directly on 6 cores, the Suricata can achieve 20 gigabits, which is pretty good. But PAMO can achieve already almost 30 gigabits. So that's like 50% improvement. The red line suggests the difference between the two systems, and from the 6 cores we currently see the decline in the difference, and we need to evaluate why. But up to 6 cores we are very optimistic of the solution and how it can help to improve the performance. Then we also tested what's the effect of the number of rules in Suricata. Of course, if you have small rule sets in Suricata, it's not that effective because you have less rules, less patterns to inspect. So you need to increase you need to make it worth for the RXP to be enabled. So with the larger rule set, it becomes better. And some conclusions on the Regex engine as a performance benchmark, let's say, and the Suricata. Yes, you can reach 51 gigabits, but you need to be careful about the other constraints, such as the inspected buffer length. That's very important. Rule set size. What are the input data? And what are your patterns? So this can all influence your overall performance. The last 3 are kind of similar across all Regex engines, whether it's hardware or software algorithm. But the inspected buffer length, saying that little buffers can take more time or can degrade your performance more than the large buffers, can be quite counterintuitive. So you need 8 Hyperscan cores, and on ARM, it's very, very good use for the ARM applications, if you have any, to accelerate the operation on ARM especially. Some personal comments about how, for me, it was to work with the Regex API. The docs, mainly the NVIDIA Doka docs, can be pretty confusing, and yeah, there are not many other materials to gain information from. So you need to be pretty careful, and you need to do also a bit of your research as well on the site to understand how things work. And that's why I hope this presentation can help for others. I really wish the RXP could have a little bit better developer debug experience, because when I messed up with something, it only told me that, yeah, there is some error, but not much more details. How we plan to continue with this work is to finish the exploration, chase the bug, and fix it. There are some other prospects, such as we only currently inspect the packet payloads, but we kind of leave the stream inspection on the table for the Hyperscan still, and we can still contribute this exploration to Suricata code as well. From industry perspective, I need to tell that the NVIDIA decided to drop support for the RXP from Doka 2.5, and in BlueField-4 we will probably have some AI accelerator instead of the Regex engine. With Marvel not offering, or we couldn't get the Octeon cards, there are no vendors currently for the Regex accelerator, so I'm hopeful that it will motivate some people to reintroduce it. If there would be possibility to have the pipeline pattern matching module on the commodity cards, that would be amazing, I think, not only for the IDS, but for other applications as well. Okay. So that's it from my presentation. If there are any questions, please ask.
Yes, here. Thank you. Did you test in Regex? There's usually needs more than one buffer. Did you? All the Regex information matched a single buffer, a single message, or you need also to sliding window with it, and you tested it with sliding windows and such techniques, or combining basically number of mbuffs together, chaining or something like this?
No, generally we didn't test this because the suricata itself was not ready to chain buffers together. So that, like, we generally receive the packet, and then as suricata, as it processes packet one by one, we evaluate the packet itself on the spot, whether we need to send it to the Regex engine or not.
Hi, yeah, thanks for the talk. I have a question regarding the performance tests you did. So you mentioned, so the performance tests on CPU were with Hyperscan, right? And you also mentioned in the beginning of the talk that the Hyperscan has a different, like, fork, maybe a vector scan, which is specific for ARM. So I'm guessing, so what I'm wondering is, did you use vector scan for the ARM testing?
Yeah.
Yes.
Yeah. It's generally, we went with the recommended approach and we used the vector scan.
Okay, thank you.
Thanks for the talk. So the setting of your problem is very similar to the one we had with ACLs and asynchronous. So I have a question regarding the Regex engine. Do you have any guarantees on the orders of the requests that you receive? Not the request, the results you're receiving back from the engine. Do you
like handling basically the reordering?
Yeah. Or do you need to do it in the app?
Yeah, not necessarily, since we mainly focused on the intrusion detection system, which doesn't send any packets any further. We didn't need to deal with the order of packets when transmitting elsewhere. With regards to the detection, from like our, let's say, knowledge, before we send it to the Regex engine, we let's say note down all the needed information for let's say detection or reassembly of other packets. So we only receive results back with the actual matches. So I don't think we had to really reorder packets as you did in your talk.
Got it. Thank you.
So did you also try Intel Hyperscan with the QuickAssist technology? So it's kind of a module to to speed up probably encryption decryption, but does it really help in this case for Hyperscan and Regex?
Sorry, I didn't get the module.
So it's a QuickAssist technology.
Okay, no, I don't think we did that.
Okay.
We just, it was either installed or compiled by hand, the Hyperscan, and unless it was doing some automatic detection, then we didn't use it.
I think for Quick Assist, sorry for interrupting, you do need a special hardware. Not all Intel chips do support it, as I remember.
Yeah. Okay.
Yeah.
Is it a CPU chip, you mean?
It's system on chip. Well, as I remember, it was a while when I used it, but it supports both modes. It could be just a pluggable PCIe card, or it could be system on chip. It depends on CPU model, does it support it or not.
Okay,
Yeah.
okay. And maybe one more remark for others. It's I think good to mention that the Hyperscan is being closed source again, unfortunately.
Wow, unfortunately. Any other questions, guys?
Hi. What's the machine you used for the testing? Because it just says ARM and 86.
The x86, the Intel Xeon Silver.
And the ARM one?
Yeah, this one.
And the ARM one?
Sorry, the ARM?
What machine was it?
The ARM machine was, it's the ARM CPU directly on the BlueField card itself. So BlueField-2 has the ARM CPU cores. It runs basically a separate operating system on the DPU itself. So that's where the vector scan and Regex engine was running.
Which version did you use of VectorScan?
I think we tried the latest, but I don't really have the information.
Just wanted to point out it's not ARM-specific VectorScan. It's all architectures, including Intel and everything else.
Okay, I think that's it. Thank you very much, Lukas. Very interesting one.